session talks about navigating the transition from relational to NoSQL. And I'm Dipti Borkar. I manage product management and product marketing at Couchbase. Our flagship product is Couchbase Server, and I oversee the product roadmap and strategy. A little bit about my background. I actually started off as an engineer writing relational database code for DB2, LUWIBM, and then managed a team for the DB2 development as well, and moved over to NoSQL. So with that, just wanted to give you an overview of the session. We'll first look at the differences, the key differences between the relational technologies and NoSQL. We'll see why people are looking at NoSQL and what are the drivers for NoSQL adoption. And then we'll take a look at the process or the transition. What are the considerations you might want to think about when you start evaluating NoSQL databases? And if time permits, I'll do a quick overview of Couchbase Server, a quick architectural view, and how the distributed document database works. So let's get started. Why transition to NoSQL? There is a huge ecosystem around relational databases. They've been around for a long time. And so why are people looking at these new technologies that are coming up? We actually performed a survey some time back, and as we talk to customers as well, there are two key drivers that seem to be the reason. The first one is a lack of schema flexibility, and so rigid schemas in the relational database. And then the second one is inability to scale out. And so let's take a look at these two drivers and how the two technologies are different from a schema, from a data model perspective, as well as a scale-out perspective. But before jumping into that, a quick look at the NoSQL catalog. So this kind of shows the different categories of NoSQL databases that exist today. By no means is this complete. There are a lot more that exist. This is really to give you a flavor of what the categories are. You see here that we start off with memcached on the side, which is a key value store, but purely in memory. And then once we start persisting data to disk, that becomes a key value database. Membase is an example of that. You have data structure key value stores as well, like Redis, which work well for data structures like lists and sets, but they are only in memory. And then when you move further towards the right, you get a lot of added functionality, and document databases in particular seem to be the most generic of these categories. So they are suitable towards a lot more use cases than some of the other ones. So today I'll focus mostly on document databases. MongoDB and Couchbase are the two most popular ones. And column family databases like Cassandra are used as well in some cases. They are column oriented in the sense that the schema flexibility may not be as good as a document database. And then finally, we have a graph database, which helps you find relationships or links within data. And so if you want to do queries like a friend of a friend, or you want to find links and relationships between objects, a graph database might be a good fit for your application. But let's take a look at document databases and what just a high-level overview of what a document database is. In general, every record in the database is self-describing. Here we see an example on the side where we have a few attributes. So we have time and server and so on. But the object itself and the document itself can be fairly complicated. So it can include nested objects, like the details attribute right here, which includes nested JSON. It could have array types where you see the tags attribute has a list of different tags that are stored as an array. And so each document can be fairly complex. And also has its own independent structure. And so every document might look very different from the other, but they're all stored in the same database or the same bucket. Now, all these documents are identified using a key, a document ID, similar to a primary key in a database. And in terms of how they are stored, they're either stored using JSON or XML or one of their derivatives. So MongoDB uses BSON, which is binary JSON, and we store JSON natively in a compressed format. So, so there's a couple of different ways of actually storing this information on disk. Now, in addition to that, what you get with document databases is the ability to index and query. And so there's different techniques for different databases that we'll take a look at in a little bit. And most importantly, the ability to auto-shard for scaling and replication for high availability. And so there are different techniques for sharding. You have range partitioning, you have hash partitioning, and different databases use different methods. Replication is available to create copies of your data, and Couchbase, for example, you can replicate to multiple nodes, and then these replicas are then available in case of node failure. So let's take a look at the data models of relational databases and document databases. Now, some of you probably work with a schema that looks like this. It's fairly complicated, lots of different tables, lots of different foreign key constraints. This is actually the gene ontology database schema. And at the moment, while NoSQL databases may not be able to replace the database behind such a complex application, depending on the type of application, depending on the type of use case, there might be some that are more relevant. There are more that are more suited. And so let's take a look at some of the simpler examples and see where how the schemas map. And later take a look at what are the use cases where NoSQL databases might be a good fit. So here you see the relational document database model, which is essentially rows and columns, and the document model right next to it. In an RDBMS, you essentially have a database. Within a database, you might have many tables, and each column has points to an attribute, and every record in the table essentially has the same attributes that are defined in that table. And so it's a pretty homogeneous structure in terms of the schema. Every record looks identical. As opposed to that, in a document model, there you could have arbitrary structure. Every document will look different, and you can have fairly complex structures. Let's take a look at an example. So here we have a user profile store, for example, and we have two tables, user info and address info. In the user info table, we have a few records. You have a primary key, and then the zip ID is the foreign key to the address info table. So typically, if you want to get all the data back, you would do a join across those two, and or specific lookups on using the key. Now, how would this map to the document model? So in a document model, first thing is all the information about a specific object is stored in one document, in the most simple case. And so here we have a document with information about me, so my first name, last name, zip, and city, and so on. But what this represents is almost a pre-computed join across the two tables, the user info and the geo info table, and and this is for the key where key equals 1. So it's you would perform a join across the two tables, get all the information about the relevant record, and so in this case, everything gets stored into one document. But now making a change to a relational database can be quite tricky. In fact, while there might be some databases that have online DDL for making changes, it is still a pretty invasive process. And so you might have many tables that represent your object or your the entity, and to add functionality, you might actually have to perform several alter table statements, which might mean a few weeks of effort to get everything right and make sure that the application works well with the updated schema. So let's say we want to extend this application and add some geo capabilities to it. We probably need to create a table, let's say country table, and then we have to alter all the other tables as well to add the foreign key, which would map to the country table, and obviously this is a normalized format, and this can be fairly invasive particularly when you need to make rapid changes to your application. And so with JSON, you can update individual records as the changes come in. And in this case, you have geolocation and country that get added on to the status information. And this might not be in another document because this information might be specific to my profile. And so every document can look different, and altering and changing schemas on the fly becomes extremely easy, which makes it easy for you to rapidly iterate over your app, so you can push out your newer versions of your app faster. Now let's take a look at document modeling a little bit and take a look at an example as well. When you start modeling your data for a document database, it's almost thinking in terms of objects. You have to think in terms of logical containers. And some of these questions might help you understand that a little bit better. So if you are storing separate objects in your modeling tier itself, or if objects are accessed together or separately, all these have an impact to how you would model your data. In general, you can either store all the details of a single object in one document, or you can split it apart into multiple documents, and we'll take a look at an example. So here are a couple of design choices. The first one, it is data is completely denormalized, which means that you are duplicating some information, but it gives you better performance characteristics because when you do a specific key lookup, you get all the information about a specific object together and much faster without any joins on the client side or on the server side for that matter. Now, if your objects are extremely large and they do not have information about and they do not have relevant information, or they are you want to split that out because they become extremely large objects, then you can split those documents out into separate docs. But then you have you might run into some issues, like objects may not be co-located. So for example, we use hash partitioning in document databases, and these objects may live on different servers altogether. Transactions are supported on a document boundary, and so that's something that you probably want to be aware of as well. And so if you're updating multiple documents at a time, that might not be an atomic operation. And in general, most NoSQL databases don't support joins at the back end, which means that to match documents or filter documents, you might have to do some additional work at the application tier. And so these are the two design options when it comes to document modeling. Let's take a look at a key selection. And so the document ID is similar to a primary key in a relational database. Documents are sharded based on this document ID. And so the Couchbase clients, for example, the SDKs will look up the document ID, hash it to a specific partition, and then locate the partition on a specific server and connect to it. So you eliminate any additional hops. And so it's pretty important to make sure that you select a good ID because that might be your primary means of looking up information. So similar to an RDBMS, you might use a UUID, which is just a sequence perhaps, or date-based IDs, numeric IDs, and so on. In some cases, you might want to use handcrafted IDs, particularly if you have related objects. You might want to actually use matching prefixes for some of those objects, so that that information is those objects can be easily looked up using those prefixes. Let's take a look at a blog example. So this is a sample app where you might have a user profile, and the user has blog entries and badge entries and so on. You have blog posts and blog comments. Blog comments are typically applied on a specific blog post and so on. And so let's see how the data would be modeled itself. Option 1. So in option 1, you have all the information stored in the same document. So now here you see you have the typical attributes that you might see in a blog document. You have the type, title, format, and so on. You might have the body as well as the actual HTML information as a part of it as well. And then you have comments. In this case, comments is an array where each of these comments are actually a part of this single document. So when you actually retrieve a blog post, it comes along with all the comments, and you can display it all together. Now, if you have an extremely popular blog, obviously it might not make sense to store all these comments in a single document. And so that's where we go into the option 2, which is a split documents or multiple documents. And here we store the ID of the comment into the main blog document. But the comment itself, each individual comment is a separate document with its ID and additional attributes that it might have. And so the application can then look at the array, go over the elements of the array, and actually fetch all the comments back out, given that we actually know the document ID for those comments. And so those are the two approaches that you could use for document modeling. Now you can extend this approach further by using lists of documents, lists of document IDs, and point them to perhaps the first comment if there's a tendency for that to be the most popular one, and if there are replies to that comment and so on. But the list can then include other additional comments that you can move over. The only thing that you need to remember is that application level joins might be needed for some of this once the filtered results are returned back to the application, given that document databases don't support that at the moment. So before I jump to the next section, which is the scaling model, let me just take a look at some of the questions that have come in. The first question is, how do you ensure data integrity in the document database? So in terms of the transactionality, we have Couchbase, for example, is strongly consistent at the document level. And so when a document is written in, there's only a single location that it gets read and written to. And so the data access is strongly consistent, and it's immediate consistency. In terms of the integrity, we persist information down to disk. We replicate information across as well. And so you have different approaches to assure durability, and you have strong consistency with the data. And the transactions are kind of at a document level. And so you have, on a per document basis, you can, the update or the insert or the delete is atomic. Moving on to the next question, is Couchbase more suitable for OLAP workloads or OLTP workloads? So that's a great question. In general, Couchbase supports interactive web apps, which means that it is either suitable for OLTP-ish kind of a workload or an ODS workload, so it's an operational data store. It might be suitable for some lightweight real-time analytics as well, given that incremental MapReduce is a part of the product. But for heavyweight analytics, if you want to do pattern recognition and a long-running job, we have a Hadoop connector, and customers use Hadoop complementary along with Couchbase to do ODS kind of workloads and the OLAP or the more heavyweight analytical kind of workloads. Question about the schema modeling itself. If the data is not in tables, when do you change the schema or add data, or do you have to update each individual document? Document has its own schema. You do update the individual documents for when updates come in, and so the attributes across all these documents may not match. This is particularly the case when you have several data sources that you have integrated into one single data store, or you have different kind of content that you're managing in a single data store. But in many cases, you might have a very simple object with the same 10 attributes that appear in all the documents. So you do have to update the documents individually, But given that a get and a set operation is relatively free in Couchbase, the overhead of then update, an individual update, is extremely minimal. So let's move on to the scaling model, and then I'll come back to some of the questions that you have. Typically, relational technologies have a scale-up model, and so let's look at the standard architecture that you might have. It's a classic three-tier architecture. Here you see you have the browsers and the end users, which might talk to the application servers. You might have a load balancer right at the top here, but the app tier itself scales horizontally, and you can add as many stateless application servers to scale your application. However, on the database side, on the back end, if you keep growing up with beefier machines and adding more RAM and adding more CPU capacity, at some point you might hit a wall, and so that's why you might see a very linear cost and performance curve for your app tier, but the database tier really isn't able to scale up, particularly for write-heavy workloads where it might not be able to handle throughput because of the complexities or the complex joins that might be being performed at the back end. Now, with NoSQL databases, most of these databases can scale out horizontally, and so along with your application tier that scales out, your database tier now can scale out as well horizontally, whether you are using EC2 instances in public cloud or you're using commodity hardware or beefy hardware. It doesn't matter. You can scale out horizontally to add nodes as your demand changes or as the number of users grow and as your workload changes. And so this enables you to get a very linear system cost because if you're using just commodity hardware, you can just add multiple servers at a time without any application downtime, and also give you linear application performance. So it gives you linear scalability where you can handle more throughput as you add more more nodes to the cluster. So now that we've taken a look at the schema modeling and how the data models differ, as well as the scale-out models, how they differ, let's take a look at what are the considerations that you might want to think about when you're transitioning from SQL to NoSQL. In terms of the process, I'm not going to go into this in great detail, but the process itself is no different from evaluating a relational database. And so you have the similar steps. You probably want to analyze your requirements, see which product solutions are a good match. You might have a performance evaluation and start beginning development and doing some document modeling and things like that, and eventually deploying in staging and production. But there's different things that you might want to consider in each of these steps. So let's take a look at what those could be. In general, what we've seen is there are 4 areas of application requirements that come up as we talk to customers, either while they're migrating from NoSQL, like MySQL or SQL Server to Couchbase, or if they're brand new applications, if they're building a completely new application, they tend to have these days very different and very complex data requirements and availability requirements. And so you might want the need to constantly update your schemas and your data sets while iterating over your application. Scalability is something you want to think about. While most NoSQL databases scale out, in terms of how easy it is to scale and how much they scale, those characteristics might be very different. And so you want to think about, do you have a known user demand, or is it not capped in any way or form? Do you need to support a viral application? Do you have constantly growing throughput, and try to understand which databases might be a good fit for that? Performance. In terms of performance, it's typically, we've seen SLAs with latencies, and so ad targeting, for example, has very low latencies. Data needs to be sent back in a millisecond, 1 or 2 milliseconds at most, and that's something that Couchbase can do with its low locking granularity, as well as its managed caching tier. And so, and then reliability. How available do you want the system? Do you want it available during database upgrades, hardware upgrades? And so these are some of the first set of requirements that you might want to think about. Moving on to the what solutions might match these requirements. If linear scalability and schema flexibility are extremely key to your application, and the other requirements are you might have ways to work around them, then NoSQL might be a very good choice for you, in particular document databases, given that they are well suited to a large variety of use cases, might be a good fit for you. But if you have more complex requirements like multi-document transactions and complex join requirements and extreme compression and so on, either you might want to look at the modeling of your data itself. Is there a way that you can model it better in terms of objects and entities without normalizing it across, so eliminating the need for most joins? If not, then a relational database might still be the best fit for your application. And there will continue to be applications, your classic order management system, for example, you should just continue to use a relational database. But there are other applications that might be better suited to NoSQL, and later on we'll just take a look at what those might be. Now, in some cases, we've seen that a hybrid solution actually works better. And so if your data depends on, or your application requirements need both these aspects, then you can have some data stored in relational database, and the data that needs to be accessed heavily by your end users, it might be content specific, it could be a user profile, for example, or it could be a session object, for example. That information can then be stored in the NoSQL database, and so you then have a hybrid approach with two different databases that back up the application. Let's move on to performance. While all NoSQL databases might talk about performance, they are not created equal. And so in terms of characteristics, look for a consistently low latencies. We like to typically see a flat curve for latencies no matter what the throughput is, and also the ability to handle high throughput. And throughput comes into there's different kind of workloads that might work better in different cases. Read-heavy workloads, for example, some databases might do a good job with it, but mixed and write workloads need a better design. And so, for example, we have a very low level of granularity, which is at the document level, which allows us to do hundreds of thousands of ops per second, even on a single node, whether it's a mixed workload or a read-heavy workload. And so that might be something you think about based on your requirements, based on the application characteristics. And so watch out for contention, heavy locking, and of course you want to see the linear scalability from a throughput perspective as you benchmark some of these databases. There are some other considerations as well that are important, and let's go through some of these, which kind of fall into the step 3, where you're trying to see what's the right match, which requirements can be met and may not be met. The first one is accessing data. And so if you are accessing, given that there isn't a standard today with NoSQL databases like SQL, there are different approaches to access this information that's stored in the database. With Couchbase, we recommend using our smart SDKs, which are cluster topology aware, and we have a bunch of them. Java, .NET tend to be more popular. PHP, Ruby, C, Python, and so on are all supported. And then we have a whole other range of community-supported SDKs as well. In terms of what might work better for you, make sure that the programming language of your choice is supported and that it's a robust SDK. In some cases, you might want to have HTTP support. At the moment, for CRUD operations, we don't support HTTP, but in the future, we will add that via some of our smart SDKs. but that's something that you might want to think about. Consistency, and this is a question that came up earlier in terms of how does it work, how consistent is the information. And so in terms of Couchbase, we are a strongly consistent system. You read and write from a single location in the system, and this allows you to have a strong consistency within your application as well. Most databases, document databases, don't support multi-document transactions, and so that's something to watch out for in general. But there are databases that are eventually consistent, like Cassandra, for the data access that you might want to, and that might have an impact on your application. Availability. So there's different ways of having availability of the system. With Couchbase, every node is identical in the system, and so we have active and replica data on every single node, which means that in case of node failures, the workload is distributed across multiple servers, and there isn't a single server that's bearing the brunt of a lot more workload. MongoDB, on the other hand, has a master-slave configuration, and so you have replica shards that information gets replicated to. It might be a little more complex to manage because there are special nodes in the system. You have to manage each node depending on whether it's a master or a slave, or maybe even a service, and so on. And so that's something you might want to think of from an operations perspective. Talking about operations, look for monitoring systems, backup and restore, upgrades, and maintenance. With Couchbase, we have a monitoring that's extremely integrated with the product, and the admin console actually gives you great visibility into all of it, ability to not only manage but also monitor information, and these are available as REST APIs, so then you can connect it to other monitoring tools and so on. Backup and restore allows you to back up across the entire cluster. You can do it cluster-wide, node, or for a specific node, for a specific partition, and so on. And all these operations in Couchbase are online, so you never take your database down, even if it's a database upgrade. So even for major upgrades like version 1.8 to 2.0, you don't actually move up with any downtime. We have online upgrades which let you swap nodes in and out for the different versions of the software. Next is scaling out. So scaling can be, while all NoSQL databases might scale, the ability to easily add and remove nodes is something that Couchbase is extremely good at. So with a click of a button, you can literally add multiple nodes, rebalance the data, all while your app is up and running, because the smart clients that I mentioned earlier actually are topology aware and will continue to get and put data information into the right partition. And then finally, indexing and querying. So in Couchbase, we use incremental MapReduce to actually build our indexes. So you can define primary, secondary indexes, or even more complex indexes or on the data. We call them materialized views. And so you can actually have code in there. We use JavaScript as the language to write these map functions. You also have the ability to aggregate across data and so on. And other databases like MongoDB have other additional querying capabilities like ad hoc querying, and so you might want to look at what works for your application, what kind of query response times you're looking for within your application. I talked a little bit about the document modeling and the document design aspects earlier, so I won't get into this phase. We will have more webinars in the future that actually go into more technical details about how you actually use the APIs and how you develop with Couchbase. But I'll leave the technical details for the upcoming webinars that we'll have. And then finally, staging and production. And so here is when you want to make sure that high availability works with replication, and that failover is supported, whether it's manual failover or auto failover and so on. And then the always online characteristics, which is really a characteristic of Couchbase, where most of the operations, I mean, pretty much all the administrative operations, whether it's index building, compaction is equivalent to a vacuum or reorg, backup and restore, all these are online, and so you don't have to take your database down for any of this. Just a quick look at our UI. And so as I was mentioning earlier, we won't have time for a demo today, but you can see that you can add multiple nodes at a time using the Add Server button, and then clicking Rebalance, you can just redistribute that information across across all the servers. You can fail over, you can remove nodes, all using the admin console. Buckets is equivalent to a database, and so you can manage this as well. We have document editing capabilities where you can look at JSON, modify it, store it back. Materialized views allow you to do indexing and querying on data. We also have cross data center replication, which allows you to do unidirectional or bidirectional replication across systems. And I'll talk a little bit about this if I get a chance to go over the Couchbase architecture. This is actually a view of our monitoring console. So here you see that you have lots of stats, almost 100 different metrics to give you visibility into what is going on at on the system. You can look at it cluster-wide. In this case, it's cluster-wide, or you can actually drop down and select a specific node and drill down into the server to see what's going on with that specific server. Before jumping into the next section, which kind of talks about use cases as well as when might it be a good idea for you to move, let me just take a look at some of the questions that have come up. Question: What are the different locking mechanisms available? In terms of locking, a lot of the locking itself is managed by the database, so that you don't need to actually manage that yourself when you're reading or writing. But at the API level, we have both optimistic and pessimistic locking capabilities. And so you can use the CAS operation, which is the check and swap, to do optimistic locking. So you can you can get access to the CAS value, and when you write it back, if there's an update, you'll know that something else has changed. And then pessimistic locking, you can actually acquire document locks on a specific document using the get with lock APIs, and that allows you to do more pessimistic locking to make sure that no one else changes that document while you're updating it. Question about the size of the data, so more on the schema side of things. Isn't the size of the database going to be larger than a relational database, since all the metadata information is repeated in every document? It actually depends on the kind of data. We use compression techniques on disk, which actually compact really, really well. And in terms of the metadata information, we don't actually store schemas, outside in a catalog or something like that. The JSON is stored natively. So whatever data you give the database, that will be stored down to disk just in a compressed format. Now, in terms of the metadata, we do store some metadata. For example, the key information, the key ID that you select, the document ID that you select is part of the metadata. Some of the other information, for example, expiry information or TTL, time to live, you might actually set a time to live per document, and you might want to expire these documents every hour or every 6 hours or so on. And so there's some additional metadata per document that's actually stored in the database. In terms of the working set is kind of your active set that you're working with. That's the only part that really needs to be in RAM for getting the sub-millisecond response times and the best performance. Obviously, you might have more data available than your memory that will be persisted to disk. Question about searching across documents. So is it difficult to search for data across documents? For example, if I have tags for the blog that I would like to retrieve all the blog entries for, how would I do that? So for that, you would use an index. You would create an index on the tags category, the tags attribute, emit all the values that are a part of that tag, and by default, the document ID will be a part of the index. And then you can query the index for a specific tag, for a range of tags, for maybe starting with B and starting with D. So you can do all these aspects using using our querying capabilities. In addition to this, we also have an integration with Elasticsearch, which is full text search. It's a search engine, and we can stream information in real time to Elasticsearch using our Couchbase plugin. This will also give you capabilities to do full text search across the entire data set. So you have a few different options of actually searching over data or querying information within your document database. All right, so with that, let me just move back to the presentation and go over some of the use cases that might work well for NoSQL and that you might be taking a look at. So these are some of the common questions that we tend to ask when you're using a relational database, where it might seem that like NoSQL would be a better fit. So for example, if you're storing serialized objects directly in the database and just using it as a key value store, you're not getting the benefits of MySQL or SQL Server or whatever database you're using, and you're neither getting the benefits of NoSQL. And so if you have a lot of sparse tables, if your application developers constantly request schema changes where you don't have much control, or you have a growing set of attributes that you want to work with, a NoSQL database, and in this case particularly a document database, will be a really good fit for your application. In terms of scalability, if you're having trouble with throughput, particularly write throughput, you're not able to achieve your SLAs with sub-second, for example, and you're having trouble managing a separate caching tier on top of your database and the relational database, and if it gets too complex, you might want to take a look at Couchbase. Couchbase is actually Memcached compatible as well, and so one of the methods of migration that we've seen is initially people might just use Couchbase as a cache because it has extremely great performance characteristics, and it has the built-in cache capabilities based on Memcached. And then over time, they would just start using it as the primary persistent store. And so this way, you get familiar with the database. You can migrate over to using it as a cache, maybe a high availability cache to replace Coherence or Redis or so on. And over time, just use it as to add more capabilities, use the indexing and querying capabilities, and so on. Now, is NoSQL the right choice for you? I mean, as I mentioned earlier, if you have pretty complex security needs, whether it's on multi-document transactions, you might want to stay with a relational database at this point, or you might have to make some compromises for doing a little more work on the application side. There are some applications that are extremely well suited for NoSQL, and let's take a look at what those, where it would be a good fit. In general, from a market adoption standpoint, we've seen all kinds of companies, internet companies, larger enterprises as well. But in terms of the use cases, Orbitz, for example, uses us as a high availability caching tier in one of the many clusters that they have. We have a lot of social gaming, ad targeting companies, and so on that use us for a user profile store or session stores. McGraw-Hill, for example, uses us for content management for their education platform. And so there are certain characteristics that are really well suited for NoSQL. Let's take a look at the data-driven characteristics. And so here if you have third-party content, particularly social media feeds, or you're collecting information from various sources like Hoover's or other news agencies and so on, and you need to store it in a single platform, Couchbase would be a good fit for that. Viral data growth. We've seen that some of the games that use Couchbase have gone viral, and within a month have had growth from a DAU perspective of 1 million to 35 million daily active users. And so you need to be able to support that kind of growth. You need a database that can scale at the back end. Changing structure, so we talked a little bit about that, and then sparse, hierarchical, variable length data is well suited as well. And then performance characteristics. So if you have SLAs of 1 millisecond, 2 milliseconds, ad targeting is a good example. You might want to look at it. High throughput, of course. If you have a large number of users and so on, you might want to take a look at it for these characteristics. I'm just going to bring up these use cases, but we'll send over the slides and you can take a look at this in more detail. Some of the different use cases, how they, what is stored in Couchbase, and what are some of the customers who are using it. This might be useful to you to see if there's something that might work that has already been done that might work well for you. Now we have about 10 minutes left, and I want to do a little bit of an overview of Couchbase Server. Mostly a technical overview, which focuses on how it works, what the architecture looks like. And so let's take a quick look at that. Couchbase is a distributed document database, and as someone asked earlier, it is better suited for interactive applications, which means that it could be mobile apps, web apps, or even in-house apps that need that have these characteristics that we looked at. And it's used as an operational data store. Version 2.0, which is a major release, came out last December, and we've received a lot of great feedback about it. At the high level, the product itself is based on the Couchbase open source project, and it's open source, Apache 2.0 licensed, and we have enterprise and community editions available. And so you can we'll always look for contributions from a user perspective and contribution code perspective as well. There's 4 key characteristics: easy scalability, consistent high performance, always on, which we've talked about a little bit, and the flexible data model, which really define Couchbase Server. In terms of the new features that we have in the release, we have JSON support, indexing and querying, incremental map reduce for some of the lightweight real-time analytic kind of workloads, and then cross-data center replication for disaster recovery, for data locality, and so on. Let's just jump into the architecture. So in terms of the architecture, every node in Couchbase is identical within the cluster. There are no special nodes, and every node has a data manager component and a cluster manager component. When we look inside, you'll see that we have the built-in cache that's based on memcached, and then we persist data to the persistence tier. We also have a query engine, and the cluster side takes care of the heartbeat within the cluster, replication across to multiple nodes, rebalance operations, failover, and so on. And so every node is identical, which is what the smart clients use. And so this might be a typical deployment that you see, web app on the front, which might be an app server or that talks to the client library, and then the client library has access to the cluster topology using the cluster map. So it can talk to any node in the cluster to get access to the cluster map. And using the cluster map, it knows where the partitions live. By default, we have 1024 partitions, and the client knows where which server these partitions live on. And so when a document comes in, the document ID gets hashed to a specific partition. It's consistent hashing, gets hashed to a specific partition, and then it knows where that partition lives, and it will directly go and access that information from that specific server. Let's take a quick look at a single node and how these operations work, and then extrapolate that cluster-wide. When a document comes in from the application server, it gets stored into the managed cache first, and at the same time, it also gets pushed over the replication queue to the other nodes in memory, and also gets asynchronously persisted to disk. This asynchronous approach is to do hundreds of thousands of ops per second, or even on a single node, given that your managed cache is strongly consistent, and we have a very fine granularity on the document logs. Now, an update operation is similar. As I mentioned earlier, we're strongly consistent, and so the doc1 prime goes in and updates the in-memory object document, and then this will get again pushed to the replication queue and then get pushed down to the database as well. For a read operation, it's pretty straightforward. We have a get API that will get you back your document if it's in the cache, and if it's not in cache, it's a cache miss, and so we'll fetch it from disk and return it back to the application. Now let's take a look at a cluster-wide approach. So when you look at it across the cluster, let's say here we have a 3-node cluster, we have active data, and along with this active data, we also have replica data, and the partitions are split across all these servers. And so document 9, for example, lives on server 3, which is a replica copy, with the active copy on server 1. Now, when you add in the Couchbase client libraries with this, you see that it includes the cluster map. And so when a request comes in for, let's say, document 5 to read, write, or update it, the clients know exactly where it lives, and it talks to that one server. And so there's no additional hops that are needed to access data. Now let's see how it works with adding nodes and how the rebalance operation works. So you can add multiple nodes at a time. In this case, we have, let's say, server 4 and 5 get added in. You can click the add server button, or we have a bunch of REST APIs for it, so you can script it out as well. And you can add servers and then hit rebalance. The rebalance operation is the one which will essentially move partitions from one server to another and will actually manage the data movement. And all this while your app is up. So as these movements are going on, the active data, document 9, for example, which was on server 1, will continue to be accessed from server 1. Once the switchover happens, the cluster map gets updated, and the new request goes to the new partitions, which might live on the new servers. And so in this case, document 6 is on server 5 and not on server 3 anymore, and you're back in. All this happens online without any application changes. And then finally, let's take a look at node failover. So when a node fails over, the active data will get promoted over to, the replica data gets promoted to active. And this can happen either using a manual failover, so we have a REST API for it, or you can click on the UI, or we have auto detection as well. And so auto failover will detect the server is down. It will promote the replicas back up to those partitions, and now you're back in business. So you have access to your data. The application servers via the clients know where the replica data lives, and will now access that replica data now that it's moved to active. I won't go into these features too much. We've had a few other presentations that go into details into indexing and querying and so on. But indexes are built on a subset of data that the server manages. You can have active as well as replica indexes, and queries that come in can go into any node in the server. So in this case, server 2 is managing the query, but any node in the server can execute a query that goes across the cluster, gathers the data, and sends the results back. We also have cross data center replication, which allows you to do unidirectional or bidirectional data transfers across clusters. The topologies do not need to match. In this case, it's just to keep it simple, I have 3 nodes on both sides, but you could have 5 on one and 7 on the other, depending on your workload and your characteristics and so on. So with that, I wanted to thank everyone, but we'll take a look at the questions, and I'll try to get to as many questions as I can. So a question about moving to NoSQL. At what volume, record, user, or transaction would you consider converting from relational to NoSQL? I would say that volume is just one of the aspects. If you are managing different kinds of data types in social media, for example, social media streams, you might be better off just using NoSQL today to start off with. And even if it's not a large volume at this point, because it's just better suited for some of those use cases. In terms of volume, it depends on how much data you're managing, what your transaction capabilities are. We've seen that customers currently that are live run anywhere from a few thousand operations per second to hundreds of thousands of operations per second across the cluster. And so it really depends on what bottlenecks you're seeing in your relational database approach. So it's hard to just kind of come up with a number or an estimate for volume, but I would say think about what is your bottleneck? Is write throughput your bottleneck? Is it the data volume that is your bottleneck? And if it is, then moving over might be a good choice. Question about referential integrity. So this goes back to the example I think I had earlier, which is how do you handle the referential integrity if a document contains the readable value, let's say country USA? How can you be sure that there isn't some dirty data that's come in? So in terms of the integrity of the document itself, an update within a document is atomic. And so if you're changing attributes within a document, that entire document gets written atomically, which means that you're sure that nothing within the document itself is dirty. Now, in terms of transactionality across documents, all NoSQL databases right now do not have multi-document statements, so multi-document transactionality. And so for that, there are things that we can do where you can simulate a transaction within the application, but that is currently one of the limitations of in this case, let's say document databases, where you would need to ensure that you would probably need to add some verification to ensure that the second update to the let's say you have separate objects has happened, so that update has happened. And so that's something, if that is of particular importance, then you might want to think about either what are there workarounds for it? Do the workarounds work well for your application? Or if it is extremely restrictive, then a relational database might be a good fit for that specific application. Question about Spring data support in Couchbase. So does Couchbase have capabilities for, I guess, the ORM or the ODM tier, if you may call it? We do have a version of the Spring data that's an early version, and we're actually experimenting that right now. We're looking for user feedback and customer feedback. And so if this is something that is interesting to you, we would like to hear from you and get your feedback. So do send me an email so that we can get you the additional information about Spring data. How can we mix, the next question is, how can we mix Couchbase with a graph / relational database or another type of database? In terms of a hybrid approach, there might be a couple of different ways of doing that. The way many of our customers use relational databases along with Couchbase is there isn't an integration at the database tier. It's really the application that's driving data access and data manipulation at the application tier. And so essentially you would issue a SQL statement on the relational database, and you would issue a get and a set statement, for example, with Couchbase, and it would be handled at the application tier. Now, there are other integrations that are coming up, for example, ETL integrations, other ways of running other query languages on top of Couchbase, and that might be the other approach that you pick. So You can use, there are a bunch of different companies and frameworks that work with Couchbase that you could use to query the information and then use that to do a join perhaps with your relational database. So that's the second approach. The third approach is a much tighter integration with the databases themselves, and that's what we are doing with Elasticsearch, for example. So Elasticsearch is a distributed text search engine which is based on Lucene, and we have a plugin for it. And so you are, in real time, you're actually sending information mutations from Couchbase to Elasticsearch. The full text search index gets built in Elasticsearch, and then you can query both these systems independently as needed. Question about the query language. So what query language is used by NoSQL databases? At the moment, there isn't a consistent language. There isn't a standard that can be used across all the NoSQL databases. We are working on a spec actually for a more comprehensive query language at the moment. But every doc, like MongoDB, for example, has a JavaScript-based language that they use. Currently, we have a REST API-based query language where you can do key lookups, range lookups, and so on. And we actually have a couple of really good blogs about how do I migrate from MySQL to Couchbase that are on our blogs, blog.couchbase.com, which actually explain how a select statement, for example, might be related to the queries that we have. So unfortunately, at the moment, there isn't one API or one language that you can use across multiple databases. Over time, though, I think, and I'm sure that that will evolve and change, and we will have more, more uniformity, but that will take some time. Now, Couchbase is also Memcached compatible, and if you have Memcached or any other caching tier, it might be a lot easier to migrate over to Couchbase because it's a drop-in replacement. You can just completely move a whole tier of Memcached or Coherence or some of the other caching solutions over to Couchbase. All right, with that, we've gotten a little over time, but I hope that this presentation has been helpful in understanding the different types of NoSQL databases, the considerations that you want to think about when you move over, when you start evaluating the technologies, the differences in the data model and the scaling model, and then finally how Couchbase works at a high level, the architecture, and the use cases that it will be good at supporting. So with that, thank you very much for attending today. If I haven't been able to get to your question, we'll try to get back to you, but do feel free to reach out to me on my email address as well. Thanks, everyone. Take care.